Before we start programming, let's talk a little bit about the background of computers. Your computers are like fancy calculators. They will take numbers, perform certain operations, and generate results. The only difference is computers only deal with ones and zeros. Now, it's very easy to convert a number in decimal to ones and zeros. Here I have the Windows calculator, the standard one, and I can change the mode to programmer. I can very easily now click on this decimal section and enter a number I want. If I want 123 converted to ones and zeros, that's binary. I just type it there and it'll show me the binary version or the conversion of that 123 into binary. So that's 4 ones, 0 and 1 1. Okay. And similarly, if I want to find out what a binary number means, I just type it over here and then I will get the answer in decimal and also hexadecimal and octal. We are not entirely interested in those other bases. So decimal 21 is 10101 in binary. So that works out nicely with whole numbers. All right. So numbers that the computer processes, they have to be in ones and zeros. And then the instructions, like the add operation that you see on a calculator, it's also in ones and zeros. So computers have what's called an instruction set. Different computers have different architectures, have different instruction sets, and the instruction set says, okay, the add operation is this sequence of binary numbers. So it'll be the binary number added with another binary number or some operation like that. And everything that you see in software is made up of instructions like that combine numbers, data with instructions. So that brings us to a few questions. If the computers can only process ones and zeros, why do you deal with things that are not ones and zeros, like text? So when it comes to things that can't be translated into binary, there are different standards that have been established that explain what numbers correspond with what data. So if it's text, there's Unicode and ASCII, and they tell you what binary numbers correspond with a particular character. For example, H or uppercase H is 1, 2 zeros, 1, 3 zeros. The space character, which is the space bar, that is also something that needs to be represented. And that's 1 followed by 5 zeros. The exclamation mark is 1, 4 zeros and another 1. So these are specified in the ASCII table. Now, this is from the Wikipedia article for ASCII, and you can find this information in lots of different places. I have shown Wikipedia here because it's easy to access. And so here you can see H is 1, 2 zeros, 1, 3 zeros, and that corresponds with the decimal number 72. And if I go over here and type in 1, 2 zeros and 1, 3 zeros, I can see that that's definitely decimal 72. So there's no magic happening. It's just converting from binary to decimal. And there is a table like this internally that says, okay, this character, slash, is this number in binary. And that's how the computer represents things that are not characters. All right. What about numbers that have the negative sign or a positive sign, or signed numbers, in other words? And what about numbers with decimal points? How do you put a minus or a plus sign in binary? How do you put a dot in binary? Now, you might think that because the Unicode or ASCII standard tells you which character corresponds with which symbol, it should be easy. It's actually not, because we want numerical values in a format that can be manipulated arithmetically. So with characters like H, we won't add H with the exclamation mark, as in we won't sum the two values up. So it doesn't need to make sense if we try to add this number with this number. It doesn't need to make sense. However, it should make sense if I try to add 1 to negative 1.234. So it has to be kept in a format that the computer can easily manipulate. So for that, there is what we call floating point encodings. So there are different standards again, but for example, this number over here is this number in binary. Now, this is basically the last place where you're going to hear this much about binary, and beyond this point, you will not see binary much anymore. And but just before that, we have one more binary horror to see. That is, what does a program look like if it's written completely in ones and zeros? Now, when a program is only in binary, we call it machine code or the machine language, because that's what the computer understands, that's what the machine understands, and we call it low-level code. So let's take a look at a simple program. It doesn't look very simple when you look at it like this. So this is a program that prints hello space world exclamation mark, no quotation marks, and so there it is. So this is not gibberish, this is an actual program that does print hello world, and I have colored this text in blue to point out that those are the binary numbers that correspond with the characters H, E, L, L, O. Earlier we said that H is 1, 2 zeros, 1, 3 zeros, and that's H. This is E, this is L, L. So you can see that these two are the same, and O space, that is 1 followed by 5 zeros, and lowercase w, and ORLD exclamation mark. So if you look at an ASCII table, you will see that those are exactly those are the exact binary numbers that correspond with this sequence of characters, the alphabetic characters. All right, so it's not gibberish, that's an actual program. It's not an exaggeration. And you can see that the Java version, which we eventually want to write, is a lot simpler. Now, it doesn't look too friendly at this stage if you just look at it by itself, but compared to machine code, it's a lot nicer. In fact, this is a very easy program to write. Now, you might think that, okay, what is this public class and all that stuff? Most of this is actually written for you, and in other words, it stays fixed, more or less. Let's try to write this program in Eclipse very quickly. So I have Eclipse open here. Now, this is how it would look when you open it for the first time. So I've just left it like that. You can uncheck this if you don't want to see this welcome screen. So I close that and I get into the Java view, and I will say I want a new Java project, or I can just say I want a project, and then I will choose Java from here and Java project. Either way, it does the same thing. I say next. Then I need to give this project a name. So the name of the project actually doesn't have anything to do with Java. The project name is only used by Eclipse. That's how it keeps different programs or different projects organized. So what I'm going to put here is I'm just going to call it my first Java program. Now you'll notice that I'm not putting any spaces in my project name, and that's not really important, but I tend not to use spaces in names of things just to be consistent. All right, so after that, I just say finish. Don't really need to say next. I can say next, and then you'll see all of these things, but I'll just say finish. And now this is not a Java program because we haven't added anything to this program, and if you try to run it by pressing the play button, it'll say the selection does not contain a main type. That's good. That means we haven't done anything with it. So if I want to add a piece of code to it, I need to add what's called a class. So what I did was I expanded my project and I right-clicked on source because that's where I want to add my code. We call it source code. So I will select class and then the name of the class. Now, one thing I have to be careful about is I am trying to replicate that exact same program shown on the slide. So the class name has to be exactly this, just to make sure that everything works fine, right? So this is called greeter. So that's how classes should be named, starting with an uppercase. There should be no spaces. It should not start with a number, and the name of the class should be like the name of an entity. We'll get into that later on. All right, so the next most important thing is to click this public static void main string args. Just by clicking that, it'll add all that code that's in the example. So that's what I said about you don't need to remember a lot of these things. So remember, I just added the name and I just put a check for public static void main. On some installations of Eclipse, it might actually show a package name and it might say it's not good to use the default package. But what we want to do right now is not complicate things, so we want to keep this empty. The package has to be empty for now. We will look into packages later on, right? So finish, and this will create my Java program. Now you can see that this is mostly the same as what we saw here, right? So that's good. Something that's different is this bit over here. Now that thing is just a comment. In other words, it has no effect to the code. We can get rid of that. All right. Next, I'm going to copy this text from here. I pressed Control-C to copy. That's the shortcut. Paste it. It fitted in nicely. Now, if it didn't fit in nicely, if it stays like that, you can fix it with a single click. You go to the source menu and you click Format. Alternatively, you can press Control-Shift-F if you're on a Windows machine. On a Mac, have a look at what keys you have to press, and otherwise just go through the menu, click Format, and it'll format it nicely. All right, so we want to keep our code formatted, and it's a very important thing. Okay, so it's showing a little star asterisk here, and that's to say that this hasn't been saved. Now you can go to File and Save, and that's also fine, but you can run the program now and it'll save it for you automatically. So it'll ask you to save and launch. You can click always save resources before launching, no problem. And when you run it, you'll see hello world. So without this line, if I remove it now, and if I try to run it, so whenever I make a change, I need to run it again. It's not going to show the changes immediately. You will not see anything. So I removed that system.out.print line, and then it didn't show me anything. But when I put it back and run it, it's showing it. So remember, if you want to make a change here, do your changes, but you need to run it again. Otherwise, it's not going to show the changes immediately. Okay, so that's how you get your Hello World program to run. So essentially, you just wrote this one line, which is the highlighted line. That also we copied and pasted. But anyway, most of these other things you don't need to memorize because they stay the same across different programs, and they are most of the time added automatically by the editor. So, all right, let's get back to the slides. Right. Now, where does Java stand in the bigger picture of things, and why should you care about Java? Right. So, programming languages are classified, and we call these classifications paradigms. If you look at various programming paradigms that are out there, you'll see that Java is actually synonymous with the object-oriented programming paradigm. And um, there are lots of other paradigms out there, and there are lots of languages. There are far more languages than there are paradigms. So you can imagine the number of programming languages that are out there. So that brings us to the next question. Okay, so there are different ways of programming, and Java is just one of those things. And why should Java matter so much? Well, Java is popular because of a few different reasons. Java has a very nicely documented application programming interface, or an API, and that's um, over here. So if you search for Java API on the Google, you'll come across this page as the first link, and you can see uh, there's a list of existing classes, or in other words, a library of features that you can use in Java. And all you need to do is to find out how something works, you just click on one of these things and it'll tell you exactly how they work. So let's look for what we know already. So we have seen system. So let's click on system, and then it shows the documentation for everything under that class. So there's a lot of stuff, and you don't need to memorize any of these things or remember any of these things, because the reference is very nicely documented. You don't see examples for everything, but there are examples for some of these things. And so that's one of the reasons why Java is extremely popular, because of the well-documented vast API. And another reason why Java is popular is because you can run a Java program across different architectures and across different operating systems. So if we look at, now this is also from the official Java Oracle website, and it shows that Java works on the x64 architecture that is pretty common in personal computers these days. It works on various versions of Windows, Solaris, which is not too common these days, Windows Server, different versions of Linux, any compatible version of Linux, and even Mac OS X, and also ARM, which is the architecture used on in tablets and smartphones these days. So it's available across lots of different architectures and operating systems, and that makes Java very appealing. So there's also there's a massive collection of tools available for developing Java. Now we use Eclipse most of the time, and you just saw what Eclipse looks like, but there's also a whole lot of other Java editing environments, or integrated development environments, or IDEs. So here's a big list that compares everything. And see, this is again under Wikipedia, comparison of integrated development environments, and you click on Java and it takes you there. So there's a lot of tools available for coding in Java, and there's also a lot of third-party usage and support for Java. If you want to find out how to do something, it's so easy to find out in Java than in some of the other languages. It's popular because it's popular. So those are the reasons that set Java apart from some of the other languages. But there are lots of different languages, lots of different paradigms, and we will be looking mostly at Java.